So this is a talk on building an industrial control system / operational technology lab. For those that don't know what an ICS OT lab is, it's like it simulates like your traditional power plant, wastewater treatment facility. If you can think of it from a physical sense, you have raw products coming in, be it water, electricity, or steam generation, and then you get a product out. Again, electricity, clean water, or reconditioned water, or like an iPhone or a Tesla vehicle. Okay, so this is all about how to build a lab and some of the issues I ran into. Okay, there's not much to know here except for I've been doing this a long time. See, 22 years. You don't need this many security certs. I'd just say you probably, if you are interested, this is a good one to get in Australia and New Zealand. And the third thing you need to know, which isn't on the slide, is if you read the talk description, you'd have found my Easter egg. Dyslexia runs in the family. So, spelling mistake for those that didn't get that one. Before I move forward with the talk, I'd just like to thank Marty, the OT guy, who lives in Tauranga. He gave me a lot of advice. In fact, he was kind of annoying, because I'd say, I want to do this, like some tanks, this process, and he's like, what, like this? And so he was always 10 steps ahead of me. He had the code done before me and the SCADA and so on and so forth. And then we've got Seth Sticks, electrician, helped me wire it. Now, for those that don't know Sparkies or electricians, this is the most electrician photo you'll ever get. Pirate flags in the background, for those that didn't see. And cigarette and a rum. So thank you guys for helping me do this. Right, well, what kind of labs or processes can we make? Well, we can do physical, purely physical, where we're actually measuring sort of physics, like how cold water is or how fast we're going to pump something. Or we can simulate the process, fundamentally. So with a simulated process, generally you've written code in the background that pretends to create the physical properties, okay? And then there's hybrid options where you're using a bit of both. Obviously, simulators are a lot easier because it's just software. Whereas a physical process, a lot more challenging. Okay, don't worry, I'll show you some examples. So a physical lab, you could use Lego. Now, for those who are quite astute, Lego doesn't really come with a process in mind, but you can drill holes and put LEDs in and run like a distribution power network and that type of thing. There's also the Lixter, I think I pronounced that right, which is a low-cost sort of manufacturing facility moving boxes like Lego blocks around. Okay, there's also ICS Village, and they do a really professional get-up. There's a photo of that coming up. And then there's mine, which I've done a tank filling process. Okay, so other sort of simulator stuff, if you're going for the software, most people go for a virtualized or container version, where the most popular being OpenPLC. You can download this through Docker or on a virtual machine, and then you can write ladder logic to get your process. There's also Factory IO, which is a 3D sort of rendering playground, if you will. You can set up your own conveyor belts and machines and robots and essentially simulate a factory. And then from a software point of view, for purely visualization, like a SCADA, there is Fuxa, excuse the language, but that's literally what it's called. Completely free, again, Docker, so on and so forth. So nice, easy virtual containers. Okay, so here I want to point out this is the one of the Lixters. Okay, you can see like there's just blocks where the block comes down and then gets put into a shelf from a lack of description. This is the, on the right-hand side, the Dragos. They are an industrial control system cybersecurity company that detects threats. And among other things, you can see that they're VC funded with the amount that cost of Lego. So a little bit jealous, but we won't go there. If I zoom in down the bottom left, this is what I mean by the Factory IO. So you can see like this is a 3D robot and it can pull boxes out, send them down the conveyor belt and end up going around, and it's quite intricate. So you can make it as simple or as complex as you like. And then finally, you can do something simple like a train track. Goes round in a circle, speeds up, speeds down. You can change the track and that type of thing. So lots of options from a physical standpoint or a simulated. Okay, most common I've seen, especially when it comes to a CTF, is due to the software and hardware requirements, most people go through the software route. It's easy to download, there's a free trial period, you can get up and running pretty quickly. So they download something like Factory.io, and then they get something like OpenPLC, and they connect them together and generate the process code and visualize it. As I was saying, there are some professional get-ups like ICS Village, which is a not-for-profit or non-for-profit. You can see there's Power Grid application here where they're demonstrating that. I believe that's WannaCry, probably someone will correct me. You've got a PLC down here, variable frequency drive. Oh, let's just circle that. And then some tank water and flow meters on the right-hand side. Very, very professional setup. Not VC funded, but a lot of these have come through donations, what have you. And it's really, really cool. You'll see this in places like DEF CON and Black Hat. A simulated one that's sort of an all-in-one, like Docker, pull, compose up, not a container guy, sorry, is, I don't know how to really pronounce this, but Graphics version 3. And it's an all-in-one sort of virtualized container, and you get a PLC, OpenPLC, a SCADA application, and this 3D visualization. And you can run simulations on it. That's not what I decided to do. I decided to do a tank system, and you can see here next to Dimitri, who took the training course last year. So thank you, Dimitri. You can see here that I've got just get down here, a PLC, a firewall, and you can see my tanks, and they basically flow down to a pump and up and around and into this. So we've got 3 colors, and then we essentially mix them. Okay, the reason I went for a pumping and water tank system is that when you mess it up with water and you pump it around, you know about it. So that process upset can be demonstrated quite easily, and that's sort of why I went this way. So all in all, it's essentially 4 coloured water tanks with 1 pump and 4 valves. Now, there's a couple of things I just want to point out. Normally, you will have, see if I can get that any closer. A little too close, whoa. Okay, well, we'll just have to go with that. What you see here, that blue thing, let's just change that. That blue thing right there is actually a manual valve. That's just to make sure that if my automatic valve, this black and silver thing, doesn't work, I can isolate and not cause a bigger mess, essentially. And then obviously we've got the pump that it connects to, and then piping with the level transmitters inside the tank itself. Okay, so that was my version 4 setup. I've been doing this a long time. The original concept I had for this sort of lab was back in 2015, where I was going to create something very, very basic with that like Factory.io and OpenPLC, and connect it through to like Kepware, do an OPC UA configuration through a firewall, and so I could teach other engineers how to get process data safely through a firewall, explain certificates, because that's what OPC UA uses. That's an industrial protocol for those that aren't aware. And that was the initial conception, and it's changed over time, and it's gotten more and more complicated as I've gotten bored, I guess. And then now I'm up to version 5, and version 4 was my old one last year. So this is the SCADA screen. Okay, a SCADA screen is literally just a visualization. Think of it like a web page, just showing you what's going on. And then we've got some ladder logic down the bottom here. Although it doesn't look much like ladder logic, it is indeed ladder. You can see an XIC there. Okay, for those that know what that is. And the whole purpose of, as I said, was to teach other people how to do cybersecurity, or at least the initial, like how to get industrial protocols through a firewall, make it a bit more secure, do some network segmentation, that type of thing. Now I use version 4 to create training content that I could put onto YouTube. Haven't released anything yet, but that's the intention. And this is my setup for version 5. Not much has changed. We still have manual valves. We still have an automatic valve, but instead of one pump, I've got 4. So each tank has its individual pump. Sounds like it's not much of an upgrade, but we'll get into that later. Okay, so this component overview of how I built this, what it cost, bit by bit, is based on the version 5. Now, you might see this one right here, version 4. This is the old pump. If we're talking about version 5, why is that pump in there? For one very, very important reason. I know it's the afternoon, people are getting tired, but this is the part you need to pay attention. It's called a peristatic pump, and if you plan to build an automatic alcohol dispenser, this is the pump you're going to buy, okay? It's the only reason it's in the slide. Right, so the pumps that I am buying for this is very, very simple. They do very, very low volume. I don't need it to pump quickly, and so 320 millilitres a minute is not that much. Okay, so I can leave it running whilst I'm training and talking about things, and I'm not going to overflow everything. So small capacity was a must. Also making sure that it was the right voltage. 24 volts is the standard DC. So I made sure that that was the case. And obviously I bought 5 of them, even though I have 4 tanks, because you always need a spare. More on that later. For those wondering what the tanks are made of, that is literally water cooling for CPUs. So there's a great benefit for this. It comes with threaded inserts so that you can twist in some of the clippings for the piping straight away. Once that's twisted in, it's pretty watertight. And you've got the options of 3 at the top, which is good, so air can escape as water fills it up. And then I can have like a manual fill or a automatic fill. And then down here, there's only actually 1 outlet. So perfect for my environment. And that's why I went down the water tank path. Also, because they're common items, they work out to be a bit cheaper. Okay, so quantity of 4, 250 New Zealand dollars. Not too bad. Already explained the manual turn-off. You always need that. Sometimes the machine decides to stop or to start, or someone in a hacking conference sends a command to make it start. So it's always nice to have that little safety feature there. As you can see, this is the valve. It's a solenoid valve. One of the trickiest things about that is you can buy solenoid valves just off the consumer shelf. Problem is that most of them are rated for air. You have to make sure that you're buying ones that are rated for water and oil, water or oil, for my purposes at the very least, because I'm not pushing air for it. If you buy one that is only air, it is only rated for air, it's going to rust out and cease to function. So that's why one of the main specs. And again, any wiring has to be 24 volt DC, as you can see with my terrible handwriting. Now the submersible water level is quite tricky. So for most water sensors, you would think in the practical world, you're like a water tank. Okay, cool, like farm water because they're off-grid. So massive, massive tank. So it can measure 5 meters of depth. Well, I've got a 30 centimeter or 0.3 meter water cooling tank. So the depth of that measurement, if I got a 5 meter rated water level sensor, means that I'm only measuring between like 8% and 12%. That's not that great. So you have to sort of find one that does actually meet your specifications. I can see there's actually a typo in here. So that's actually 100 centimeters, not 0 to 10 meters. Is the specific one that I got, okay? Because, 1 meter, 100 centimeters, 1 meter of depth. So that means I'm only measuring 30%, from 0 to sort of 30%, but that's still a lot more of a range than what you can find. So that was one of the hardest things to spec, and took numerous amounts of planning to get right. People have made their own water level transmitters, but they generally can be quite expensive, even if you DIY it. So this is what I went with, because it's sort of fit for purpose, but not quite, but good enough. Okay. These inserts, so if we go back to the version 5, every sort of screw that's sort of mounting, you can see there, this cable tray is mounted. There is a threaded insert behind it, okay, because this is, what's on the back here is clear perspex, or misty perspex, and you don't really want to be drilling, undrilling, there's a chance of cracking. So you generally put in a pilot hole and then you get the threaded insert in, and it holds it quite firmly. So that's another piece of the kit. Pneumatic fitting tubing. So as you can see, again in the photo, all these tubes, actually it's probably better to go to this one. You can see the lineup. There's a tube, another tube, and connectors. So those are all various, and so I just sort of lumped them all together, you know. An entire pack, I think, cost, $58.22. Okay, so they're pretty cheap and easy to access. Some of these are optional. So the reason they're optional is you don't always need a firewall for this. As I'm doing mine for teaching and demonstrating like network cybersecurity and segmentation, I kind of needed a firewall, so I made sure I had one of those. But if you want to build one, you can see it's quite an expensive item at $3,000, so you might not want to grab that. The next thing is a Rio card. So if you have your PLC up the top here, you can connect it to a Rio card, and that basically means all the instrumentation wires into this, and then you can have Ethernet comms that essentially sends the data out. PLC still controls the Rio, stands for remote input, output, and I wanted to demonstrate that because that's what I see typically in an industrial environment. But most PLCs come with input and output cards, so you don't really need that if you wanted to cheap it. That's why it's, again, optional. And then finally, you will need an actual engineering workstation. Seen as most PLC or SCADA software runs on Windows for historical reasons, we won't go into that. I bought a NUC with lots of RAM, so I could run virtual machines, containers, that sort of thing, and Windows 11, okay? Now I actually lost the receipt, so I went in and I basically spec'd it up. So this is what I'd buy today if I was going to do it again. And then finally, the PLC. So this one is not the one that I used in version 4. As you can see here, this is a different one. This is an Allen Bradley Micrologics. Nothing wrong with that PLC, but I had a specific use case. And so I went for the Phoenix Contact one. As you can see here, this is what you call a starter kit. So it comes with push buttons, pre-wired. You can see it wired coming into there. You've got an analog input. So this is sliding from 0 volts to 10 volts. And as it slides, it changes its value inside the PLC. Okay, so when selecting cards, there's 4 there. There's slot 1, 2, 3, 4. You can tell by the orange tabs that I've written over. So when you're speccing your PLC, you need to know that you've got the right input and output cards. So an input card is a switch coming in, and an output card is something that you turn on, like a relay, or a solenoid valve, or a lamp, light, if you will. So those are digital, they're binary, like 0, 1, true, false, off, on. And then you have analog with the values, like I was talking about there. 0 volts to 10 volts, that's basically a representative number. So it's an analog value. And once again, you have analog inputs, like how hot is this thing, and then an analog output, like how fast do you want it to now go. Okay, all standard in process control. But basically when you buy your PLC, you have to then sort of go through and go, do I have the right cards for digital and analog? Do the instruments match? Are they compatible? Are they on the same voltage? Do they understand each other? And so there's this massive process of trying to make sure that that is correct before you even purchase it. you get that wrong, then it's going to cost you a lot of money. So as you can see here, this cost me about $2,000 roughly. But the key word here is starter kit. So when you type in like PLC starter kit in Google, these are the cheaper brands. They're designed, not cheaper brands, they're designed for people to get their hands on it with a cheap license so that you can get used to the system and the software. Okay. If you went out and went to a system integrator, say, can I please have like Rockwell Automation, Allen Bradley engineering software, they would be like, absolutely. That will be $11,000 to $20,000 a year. Of course, you probably won't be doing that. So picking the right PLC through a starter kit usually means that the license cost is a lot lower. And in this one in particular, the PLC Next platform, the engineering software or IDE software is free. Okay, finally we're getting down to the absolute total. And this table is a miscellaneous of stuff. You know, it's like fuses, terminal boxes, crimping bars, jumper bars, ferrules, as you can see there, massive list, kind of boring, and I guarantee you I've missed stuff. So at the bottom there I've added 20% contingency for tools that I had to buy or misplaced or what have you. So the total was practically $11,000. Realistically, you're probably going to be spending $13,000. Now, if you asked me if I went down this path that I was going to spend $13,000, would I still go this way? Absolutely not. I would have bought the Lego. It would have been way better. But you don't know that until you try, right? So, cautionary tale. And just once again, I want to reiterate the fact when it comes to the software, it's actually the licensee is one of the biggest problems. Like Windows 11 Pro, you could probably get a hold of that. The PLC Next engineering software, that is free for that particular PLC. And they're generally branded. So you can't use PLC Next engineering software on an Allen Bradley or Siemens PLC. It doesn't work like that. You have to get the vendor's specific engineering software. So that is a crucial factor for picking your PLC for this lab. And then you've got the Ignition server, which is a SCADA server, very, very popular. One of the best things about it is it runs for 2 hours, fully featured. You can do everything you want with it, and then it will turn itself off and say, your license doesn't allow you to continue. Please click this reset button and you'll get another 2 hours. Or you can turn your computer off and on again. So that is enough to demonstrate what a SCADA server looks like and how to operate it for my training purposes. And as I said, Ignition is everywhere in the industrial world. So it's sort of good from a training perspective because it is what you'll see out in the real world. That's why I chose that one. But there are others like Kepware and Metricon. Okay, so problems and challenges encountered. Instrumentation selection, already sort of went through that with the PLC process. It was a bit of a struggle because you've got to think of everything before you buy. So it's like, I want this instrument to fit into my tank, and then you're like, I want this PLC, but this PLC doesn't come with this card, and then that card to make this connect will cost me $500. It's like, oh, well, that doesn't work. So I've got two options, change the level transmitter or change the PLC. So getting that through, I had numerous conversations with Marty, the OT guy, about getting all that right. So he was great help there. Another problem is budget. As you can see, it's quite expensive, or I feel like $13,000 is pretty expensive. And someone's got to pay for that, you know. Fortunately, my wife doesn't know, so... Time to take building this thing. Obviously, I've got a full-time job and trying to run a business, all those things, family life, being a dad, being a husband. It takes a lot of time to build and maintain and get this thing going. So those are obviously pretty standard problems to come across. Now, I've already stated that engineering software is one of the biggest problems, like that 11 to 20K for programming a simple PLC. But I just wanted to make sure it was on the slide so that I didn't forget. It is very, very cost prohibitive to learn about how to do ICS/OT. if you follow the traditional route. Okay, so one of the things I did was, again, this is a starter kit, this is a Schneider one, and it did not come with the right function codes in order for me to communicate with my Rio. Now, I'm a professional control system engineer. I know how to write the function blocks to get those codes to work, but I was looking for a more drag and drop, click and play solution because I'm time poor. So this is Geralt. Geralt's about to say a word, not literally. I'm sure you can use your imagination. That's how I ended up with the PLC Next. It had a much better interface to do what I wanted, so I chose that. Once again, the compatibility, what you think is going to happen and what actually happens is usually two different things. So right off the bat, I chose the wrong PLC for my application. That cost me $2,000 that I wasn't expecting. Another problem was the variable speed. So you notice that I chose 4 pumps on version 5 and that was the only change. Well, the plan was to make sure that those pumps weren't just on or off, they were variable, meaning I could say go 50%, go 70% faster, go 100%, and really, spruce it up in terms of having a process. But in order to do that, you need a PWM board, okay? PWM board, as I said before, the 24 volts DC is standard, so I made sure that this was 24 volts DC. What I didn't realise was to actually power the device, it was 5 volts, which I didn't have. So that really put a damper on things. It's like, okay, it's not a huge problem. We can fix this. There are things called DC to DC converter. So I had a 24 volt DC power supply system. I needed 5 volt. I can buy a DC-DC converter, and then I can make this modulate my pumps. So the first problem was the 5 volt. It's all right, I've got to fix DC to DC converter. Cool. Attach it, wire it, everything's going great. Then, what's that smell? Oh shit. Hit the e-stop, pulled the power. Yeah, another problem. So I had to essentially revert back to a very simple on-off pump system. Okay, more problems. If I had the time, if I had the budget, I'd probably just buy an all-in-one pump system. But alas. And the other thing is what I really wanted to show you guys was a complete working system with a video, what have you. Unfortunately, if we go back to, you can see that this is unwired and it's mostly together, but it's not fully there. PLC's missing and so on, is that the fragility of some of the instruments is actually quite hard. So they are so sensitive that even like a slight knock can actually break the instrumentation. One of the plastic pieces fell off the pump, but it's all right, got a spare. One of the valve plastic connectors cracked, and now I've got water leakage. So having a physical process, great, but there's all these like little things that have to go right for it to work. Okay, so my advice, you do not need a physical process to create an ICS and OT lab. Hopefully I've demonstrated why. I built this way so I could teach cybersecurity and have that realism, all right? But you can get away with OpenPLC or alternatively CodeAssist, that runs for 2 hours, complete PLC system. You can use ignition servers for your SCADA, again, 2 hours, Tatesoft, SCADA system. So there's 2 there. So that's OpenPLC, CodeAssist PLC, all free, all can download and run for 2 hours. Inductive automation, and then Tatesoft. Those are 2 separate SCADA systems, again, free, run for 2 hours. Docker containers and networking, you can pull OpenPLC and CodeAssist through a Docker and a container and get those working. You can pull ignition servers and Tatesoft framework SCADA server through containers and get those running. Right, very, very easy process running that Docker pull thing. And then there's complete systems like that one I showed you, Graphics version 3, cyber physical simulation. Right, and all you need is a laptop. It will run on most laptops. If you want to learn about ICS OT and have that sort of lab, this is all you need to actually really understand it. So you don't need fancy, you don't need expensive. As I said before, if you want that sort of 3D, real looking, this is this is a process happening in a manufacturing workshop. You can see the boxes going through. It does look very, very nice and aesthetically pleasing. Okay, so Factory IO has a trial, and the actual software that runs this is actually pretty cheap. Lifetime purchase, and also an annual one if you want it even cheaper. You can get some really, really good systems here. It can run on OpenPLC, it can run on Codesys, it can run on real PLCs, like Siemens here, Allen Bradley, Telesys connected to actual IO here. So this is actually simulating a physical process from the Factory IO. So Factory IO essentially talks to this and simulates the on-off inputs, outputs, analog transmitters. Those all go into the PLC, and then the PLC executes the code. So once again, hybrid as well. So plenty and plenty of options. But if you do want something a little more complicated, like a physical process, the train system's very, very good and easy to do. Wish I did it. But yeah, it's on, off, track change, speed up, speed down. If you're VC funded, Lego City, pretty cool. And then a small factory plant like the Lixter. Okay, so key takeaways. Physical processes are hard. They're very time consuming and expensive. I'd say worth it though. You could do a lot with free. Even if it only runs for 2 hours, you can do a lot with cheap software, free software. And finally, if you're doing this for ICS, OT, cybersecurity, and trying to understand how a device performs and connects, and building a lab will teach you a lot. Even if you're just interconnecting and using somebody else's sort of templates, you can still learn a lot from how physical systems, cyber systems work. So, and that's it. So.
I am a super genius.